One evening in the spring of 1940, in a quiet building at Princeton University, a telephone rang. A young graduate student picked it up. The voice on the line belonged to his professor, and it skipped every pleasantry. "I know why all electrons have the same charge and the same mass," the professor said. The student asked why, and the answer he heard has never entirely left physics, because they are all the same electron. One electron, not one kind, one single particle, the professor meant, threading its way forward and backward through time so many times that it looks, from where we stand, like every electron in every atom, in everything that exists. The student laughed and found an objection within seconds. The professor waved it off. Neither of them wrote the idea down that night, and yet half of it went on to win a Nobel Prize. And the other half became one of the strangest questions anyone has ever asked about the universe. Because here is what makes the idea refuse to die. Every electron ever examined is perfectly identical to every other. Not similar, identical as far as our finest instruments can tell. So the question the phone call left behind is simple to say and very hard to put down. If nothing in nature can tell two electrons apart, how sure are we that there are two? The man on the phone was John-Archibald-Wheeler, one of the great physicists of the 20th century, the man who would later give the black hole its name. The student holding the receiver was Richard Feynman, 21 years old, not yet famous, not yet anything, just a sharp young mind that Wheeler liked to think out loud at. The two of them had fallen into a working rhythm that would quietly shape the next 50 years of physics. Wheeler generating ideas the way a bonfire generates sparks, most of them dying in the air, a few landing somewhere dry. Feynman catching each one, turning it over, and telling him, with a directness professors rarely enjoyed, whether it held together. Colleagues who knew them said the arrangement worked because neither man took offense. Wheeler expected most of his sparks to die, and Feynman enjoyed nothing more than checking. A late phone call with an outrageous claim was not an interruption of their work, it was the work. And to understand why Wheeler said something so outrageous that particular evening, you have to feel the puzzle he was trying to solve. Because the puzzle is real, it is sitting in the room with you right now, and physics has never fully explained it. Start with something ordinary. Look at any two things in this world that are supposed to be the same. Two snowflakes, famously, are not. Two apples from the same tree differ in 1,000 small ways. Even two ball bearings from the same machine, polished to the same tolerance, carry different scratches under a microscope. Everything made in this world comes out slightly different, because everything in this world is assembled, and assembly leaves fingerprints. Now go smaller, down past the apple, past the cell, past the molecule, into the atom, and find the electrons. And there the pattern breaks. Every electron has exactly the same electric charge, exactly the same mass, exactly the same tiny magnetic personality. Physicists have measured that magnetic property to a precision of 13 digits, roughly the precision of measuring the distance to the moon, and being off by less than the width of a hair. And every electron agrees with every other, digit after digit after digit. There are no worn ones, no factory seconds, no slightly heavier ones from a bad batch. In a universe where no two grains of sand match, the electrons match perfectly, all of them, everywhere, always. Pause on how many we are talking about, because the number matters to the puzzle. Take 1 teaspoon of water. In that teaspoon, there are more electrons than there are seconds in the age of the universe, comfortably. Scale up to your body, an ocean of them. Scale up to the observable universe, and the estimate physicists use is a 1 followed by roughly 80 zeros, a number with no name in ordinary speech. More electrons than there are stars by an almost embarrassing margin. Now hold the two facts side by side. A quantity beyond all counting, a sameness beyond all measuring. Any process you have ever seen produce many of something, casting, printing, growing, copying, gets sloppier as the count climbs. Errors pile up, variation creeps in, entropy takes its tax. The universe has made 10 to the 80 of these things, and the tax was never collected, not once, not anywhere. Whatever is producing electrons is not producing them the way anything you know is produced. Here's the strange part. They do not just match, they are indistinguishable in principle. This is worth a slow beat because it is one of the deepest facts in all of science. With snowflakes, you could in theory tag one, photograph it, follow it. Two identical twins can be told apart by a fingerprint, a freckle, a filling in a tooth. Even two printed copies of the same book differ, if you look closely enough, in the microscopic lay of the ink. With electrons, nature provides no tag to read. There is no serial number, no scratch, no birthmark, and no experiment, even a perfect one, that could label an electron now and pick out that same one later from its neighbors. Ask what happens if you try. Suppose you watch one electron very carefully, determined never to lose sight of it, and a second electron passes close by. The two approach, interact, and separate, and here is the uncomfortable truth. The question of which outgoing electron was yours has no answer. Not an unknown answer, no answer. The universe simply does not keep that information. It is not that we have failed to find the labels, it is that, as far as physics can determine, the labels do not exist, and nature's own bookkeeping is written without them. Could a scientist simply shrug at this? Just accept that electrons are identical, write it into the rulebook and move on. In practice, that is mostly what the field did for years, and the shrug even has a respectable logic. Every science has starting facts it does not explain. But great physicists tend to be constitutionally unable to leave a perfect pattern alone, because in their experience, perfect patterns are never free. When every copy of a newspaper in a city says exactly the same thing, down to the last comma, you do not conclude that 1,000 scribes achieved miraculous agreement. You conclude there was one printing press. Sameness that absolute is usually the fingerprint of a single source, a shared origin, a common machine humming somewhere out of sight. The question was never whether the electron's sameness had an explanation. The question was what kind of press could possibly be printing them. So a fair question forms, the one Wheeler was answering that night. Why? Why would nature produce 100 billion, trillion electrons? More electrons than trillion electrons. More electrons than there are stars, than there are grains of sand, than there are drops of water in every ocean, and make every single one a flawless copy. What kind of process produces perfect sameness at that scale? When a puzzled mind meets perfect copies, it reaches for a familiar thought. Perhaps they are copies because there is an original. And Wheeler, that evening, reached further than anyone before or since. Perhaps they are not copies at all. Perhaps you have been meeting the same one, over and over, all along. To see how that could even be imaginable, you need one idea, and it is a beautiful one. The world line. Physicists like to picture time as if it were laid out like the pages of a flipbook, every moment a page, the whole book existing at once. This is not just a drawing trick. It is how Einstein's relativity naturally describes the world, with time as a direction you can map, like the pages of an album that already contains every photograph. In that picture, you are not a dot moving through the world. You are a long, winding path drawn through the book, from the page of your birth to the page of this evening, one continuous line through space and time. Everything that exists draws such a line. A stone draws a short, straight one. The Earth draws a vast corkscrew as it circles the Sun while the Sun circles the galaxy, and an electron draws a thin, wandering thread of a line across the pages of the universe. Why bother with this picture at all? Because certain questions become easy in it that are impossible without it. Ask how many people are in a family, and a photograph gives one answer. Count the faces on the page. But ask the same question of the family album as a whole, and something subtle appears. The baby on the first page and the grandmother on the last page can be the same person, photographed 70 years apart. Counting faces page by page overcounts the people, because one life can cross many pages. Wheeler's whole idea lives inside that subtlety. When we count electrons, we are counting faces on today's page of the universe. The question he asked is whether many of those faces might belong to one very long life. Now picture a single strand of holiday lights, one wire, threaded through a dark house, up the stairs, through one room, back through another, looping past the same window 3 times. Stand outside that house at night and look at one window. You see 3 lights. 3 separate, distinct lights, you would swear. But there is one wire. The 3 lights are 3 crossings of a single strand that bent back on itself behind the wall where you cannot see. Wheeler's idea in one image is that the universe is the window and the electrons are the lights. One world line, folded back and forth through time in a pattern too vast to trace, would cross the page of any single moment countless times. Each crossing would look like its own electron. The many on this picture are one line, seen again and again. But a folded line has to fold, and this is where the young man on the phone earned his keep. When the line bends back, when it turns around and runs against the direction of time, what would that backward stretch look like to us, who only ever watch the pages turn forward? Wheeler had an answer ready, and the answer is the piece of that phone call that turned out to be pure gold. Running backward through time, he said, the electron would look like a particle with its electric charge flipped. It would look like a positron, the electron's mirror twin, its antiparticle. And the remarkable thing, the reason this was not simply dismissed as a game, is that the positron is real. It had been discovered 8 years before the phone call, by a young experimenter who was not looking for it at all. His name was Carl Anderson, and in 1932 he was at Caltech in his mid-20s, photographing the trails left by cosmic rays, particles that rain down on Earth from deep space in a thin, ceaseless drizzle nobody feels. His instrument was a cloud chamber, one of the loveliest devices in the history of science. A chamber of vapor on the edge of condensing, so that a passing charged particle leaves a thin, visible track of droplets, the way a jet draws a white line across a cold sky. You cannot see a particle, you can see where it has been. A magnetic field ran through Anderson's chamber, and the field bends the path of anything electrically charged. Negative particles curve one way, positive ones the other, and the tightness of the curve tells you how light or heavy the traveler is. Anderson knew the curl of an electron the way you know your own handwriting. And one day, on one photograph, there it was. A track with the exact lightness and grace of an electron, curving the wrong way. Now feel the moment as he must have. The easy explanations line up first. A proton? No, a proton's track is heavier, blunter, wrong in the curve. An ordinary electron traveling upward instead of downward, fooling the geometry? That one nagged, so Anderson did the careful thing, the thing that separates a good experimenter from a lucky one. He placed a lead plate across the middle of the chamber. Any particle punching through the plate loses speed, and a slower particle curves more tightly, so the 2 halves of the track would betray the true direction of travel. He waited for another wrong-way traveler, and it came, and it crossed the plate, and the tightening curve settled the matter beyond argument. The particle was light as an electron, charged the opposite way, and real. He had photographed a positive electron, the first piece of antimatter human beings ever knowingly saw, and it earned the name positron. 4 years later, at 31, that photograph carried Anderson to the Nobel Prize. So by the time the telephone rang in 1940, the ingredients were all real. Electrons, perfectly identical, all of them. Positrons, their mirror twins, genuinely existing, genuinely rare. And Wheeler's proposal stitched them into one picture. The positron is not a second kind of thing. It is the same electron on a backward stretch of its one enormous journey. Forward through time, we call it an electron. Backward, we call it a positron. One traveler, two directions, countless appearances. Why does this matter? Because if that picture were right, it would answer the sameness puzzle in a single stroke. Why is every electron identical? For the same reason, every footprint in a looping trail across a snowfield fits the same boot. You do not marvel that 10,000 prints in the snow all match perfectly. You realize there was one walker, and the field is simply large and the walker was thorough. Wheeler was suggesting that the universe is a snowfield, and that the prints we call electrons, all 100 billion trillion 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 of them, were left by a single traveler with an unimaginable amount of time on its hands. And Feynman, 21 years old, heard all of this in real time on the phone and asked exactly the question you may be forming. It is the right question. If half the crossings of that folded line run backward, then the universe should hold about as many positrons as electrons. Half the lights in the window should be the mirror kind. But look around. The world is made of matter. Electrons are everywhere, in every atom of every rock and tree and person. Positrons are so rare that Anderson needed particles falling from space to catch even one. But Professor, Feynman said, there aren't as many positrons as electrons. And Wheeler, unbothered, offered only a shrug of an answer. Maybe they are hidden somewhere, and moved on. The objection was left standing that night. It stands to this day, and later in this story it will return with a precise number attached, a number that decides whether the idea can live. Hold on to it. Yet here is the turn that makes this one of the best stories in physics. The idea did not need to be right to change everything. Sometimes a wild guess contains one true gear. 25 years later, in December 1965, Richard Feynman stood in Stockholm accepting the Nobel Prize in Physics, and in his acceptance lecture he told the world about that phone call, word for word, the way we have told it here. He did not believe the universe held a single electron. He never had. But the other half of the idea, the backward-in-time picture of the positron, he had taken with him and kept. I did not take the idea that all the electrons were the same one as seriously, he admitted, as I took the observation that positrons could simply be represented as electrons going from the future to the past. And then, with the grin you can hear even on the page, that I stole. What he built with the stolen half, and what it revealed about the deep bookkeeping of reality, is where this story goes next. Because the backward-in-time picture was about to be tested in ways neither man on that phone call could have imagined. Against machines that weigh a particle's magnetism to 13 digits. Against twins of matter and antimatter compared atom by atom. And against one experiment where two identical particles of light met on a half-silvered mirror and did something no separate things should ever do. Before we follow the history further, one habit of this channel: pause and make sure the picture is genuinely comfortable, because the next stretch builds on it. The claim on the table is that a particle's path through the flip book of time could bend backward, and that the backward stretch would appear to us as antimatter. If that feels impossible to visualize, try it with sound. Record a spoken word and play the tape in reverse. The sound is unrecognizable, alien, and yet it is not a new recording. It is the same information read the other way. Wheeler's proposal was that a positron is an electron played in reverse, the same entity read against the grain of time. Whether nature actually reads tapes backward is exactly what the rest of this story tests. What you should carry forward is only this: the idea is strange, but it is not sloppy. It is precise enough to be checked, and physics has spent 80 years checking. To follow the stolen idea's journey, wind back 12 years before the phone call, to 1928, and to a quiet Englishman named Paul-Dirac. Because the positron did not enter physics through a telescope or a cloud chamber. It entered through arithmetic, and it entered uninvited. Dirac himself was a man of legendary economy, an engineer's son from Bristol who spoke so rarely and so precisely that his colleagues joked about it in units, and who trusted mathematics the way other people trust their own eyes. Dirac was doing something that sounds simple and was not, writing down the rules for how an electron moves when it travels close to the speed of light, where the older quantum rules and Einstein's relativity had to be made to agree. He succeeded, and his description of the electron turned out to be one of the most accurate pieces of science ever written. But it came with a passenger. The mathematics kept producing a second answer alongside the first, a shadow solution describing something like an electron with its properties mirrored, and no matter how Dirac tried, the shadow would not leave. Most scientists, faced with an unwanted answer, quietly discard it the way you discard the negative root when measuring a length. Dirac had the strange courage to take his shadow seriously. By 1931, he had concluded that the mathematics was trying to tell him about a real particle, a mirror electron no one had ever seen, and he said so in print. 1 year later, Anderson's wrong-way track appeared in the cloud chamber in Pasadena. Anderson, remarkably, was not even chasing Dirac's prediction. The shadow found him anyway. Sit with how strange that sequence is. A man rearranging symbols on paper in Cambridge insisted the universe owed him a particle, and the universe, within a year, paid up. When people say mathematics is the language of nature, this is the kind of story they mean. It helps to know what picture the backward-in-time idea was competing against, because the reigning explanation of antimatter in those years was one of the strangest constructions ever taken seriously, and it came from Dirac himself. To make sense of his equation's shadow solutions, Dirac proposed that what we call empty space is not empty at all. It is completely full, packed everywhere with unseen electrons, occupying every available low state, the way a parking garage can be so uniformly full that you stop seeing the cars and just call it the garage. On this picture, a positron is not a thing, but an absence. Knock one electron out of the full garage, and the empty space left behind moves around, carries an effective positive charge, and behaves exactly like a particle. A whole promoted to an entity. The astonishing part is that this bizarre bookkeeping worked. It predicted pair creation and annihilation before anyone saw them. But it creaked. It asked you to believe in an infinitely full, invisible ocean of particles underlying everything, and calculations built on it kept tangling, and a generation of young physicists, Feynman loudly among them, found it maddening to work with. The backward-in-time picture swept all of that away in one stroke. No packed vacuum, no promoted absences. A positron is an electron on a reversed stretch of road, full stop. Where Dirac's picture explained antimatter with an infinite hidden crowd, the Stueckelberg-Feynman picture explained it with a single change of direction. Physics, given the choice between an infinitely full basement and a U-turn, took the U-turn and never went back. Why does this matter for our story? Because it shows what the phone call's stolen half actually accomplished. It did not merely rename the positron, it deleted an infinity from the world picture of physics, replaced the fullest imaginable vacuum with an ordinary empty one, and made antimatter a statement about geometry, about the direction of a path, rather than about hidden substance. Ideas that delete infinities while explaining the same facts are the rarest currency in science. That is why Feynman grabbed it, and why it stuck. So antimatter was real, and physics now owned two facts that did not obviously fit together. A mirror particle existed, and every electron was identical. The first person to connect them with time itself was not Wheeler, and this part of the story deserves saying plainly, because history nearly forgot the man. His name was Ernst-Stueckelberg, a Swiss physicist from an aristocratic Basel family, and in 1941, 1 year after the Princeton phone call and entirely independently of it, he published the idea properly. An antiparticle can be understood as an ordinary particle whose journey through time has reversed direction for a stretch. a single path whose time coordinate advances and retreats, with what looks like the birth and death of particle pairs being nothing but the path's turning points. Where Wheeler had tossed the thought into a telephone and moved on, Stueckelberg worked it out with care, inside proper mathematics, and put it on the record. Life was not kind to him. His first breakdown came in Princeton in 1932, of all places, the same campus where the famous phone call would ring 8 years later. For the rest of his life, he struggled with severe mental illness, enduring repeated hospitalizations that his biographers say seriously handicapped a career that should have been one of the century's most celebrated. Again and again, he arrived at foundational ideas early, sometimes first, and watched the recognition flow elsewhere while he recovered in a clinic. He came close to Nobel recognition and never received it. Science tells itself it remembers ideas fairly. Stueckelberg's story is the quiet counterexample, and it is worth one beat of honesty in any telling of this history. The backward-in-time picture that carries Feynman's name in every textbook was written down first, and written down properly, by a man most people have never heard of. Why does this matter beyond fairness? Because it means the backward-in-time picture was discovered twice, independently, by two very different minds looking at the same physics. When that happens, it usually means the idea is not a whim. Something in the structure of nature was pointing both men the same way. There is a further piece of context that explains why Wheeler, of all people, was primed to make his leap, and it is a lovely sidebar in its own right. Wheeler and Feynman, in those same years, were deep in a joint project about light itself, wrestling with an old embarrassment. The mathematics of electricity has always offered two families of solutions: waves that ripple outward into the future, which everyone uses, and waves that ripple backward from the future into the past, which everyone politely discards, the way you discard the second answer when a square root offers you 2. Wheeler and Feynman asked the forbidden question: what if you keep both? They built a version of electromagnetism using half of each, forward and backward waves in perfect combination, and showed, remarkably, that in a universe full of absorbing matter, the backward waves conspire to hide themselves, leaving exactly the ordinary world we see. The theory was eventually set aside. The mainstream solved its problems by another road. But notice the habit of mind it reveals. In 1940, Wheeler was a man who had already spent months taking time-reversed solutions seriously as physics rather than as mathematical debris. When he looked at the positron, he was already wearing the glasses that made it look like an electron in reverse. The one-electron guess was not a bolt from nowhere. It was the boldest sentence of a conversation he was already having with the universe. Take a moment with the pattern that keeps recurring in this story, because it is a genuine lesson about how physics moves. Twice now, the discarded half of the mathematics, the shadow solution, the backward wave, turned out to be the door. Dirac's unwanted second answer became antimatter. The unwanted backward waves became, in Wheeler's hands and then Stueckelberg's and Feynman's, the modern picture of every antiparticle. Nature, it seems, writes with both halves of the pen, and the history of 20th century physics is partly the history of scientists learning to stop crossing out the half they were not expecting. And through the 1940s, the man who turned the pointing into a working machine was the student from the phone call. Feynman took the picture seriously as a tool. If a positron behaves in every calculation exactly like an electron running its stretch of road in reverse, then you can compute with it that way, and the computing becomes astonishingly clean. In 1949, he published the method, and out of it came the diagrams that now carry his name, and they deserve a moment because you have probably seen one without knowing what you were looking at. A Feynman diagram is a small cartoon of a particle encounter, a few lines meeting at points, drawn in a plane where one direction means space and the other means time. Read upward and you are watching a story unfold. Two electrons approach, exchange a flicker of light, and part ways changed. What made these doodles revolutionary is that they are not just illustrations. Each one is a precise bookkeeping device, Draw every diagram a process allows, follow simple rules for what each line and joint contributes, and out comes a prediction you can take to 13 digits. They compressed calculations that once filled notebooks into pictures a student can sketch on a napkin, and physicists have been sketching them on napkins, blackboards, and conference tablecloths ever since. And inside every one of those diagrams, to this day, an antiparticle is drawn as its particle running against the arrow of time, an arrowhead pointing the wrong way down the page. Wheeler's phone call is drawn, literally drawn, millions of times a year, by people who have never heard the story. The wild half of the call was quietly forgotten. The stolen half became the standard language of particle physics. Picture the bathroom scale trick, because it is the cleanest way to hold on to what renormalization means, and it comes almost straight from the history. Suppose your scale is broken in a peculiar way. It always reads 80 kilograms too high. Useless? Not quite. Weigh yourself, weigh your suitcase, weigh the cat, and every reading carries the same enormous, consistent error. So you do the obvious thing. You weigh nothing at all, note the offset, and subtract it once, forever. From that moment, every measurement the broken scale gives you is perfect. The infinities in the equations of electrons and light behaved like that offset, enormous, alarming, and always the same, always attached to the same few quantities. Subtract them once, anchor those quantities to their measured values, and every further prediction comes out finite and right. That is the move Bethe found on the train, and the reason it matters for our story is what it tells you about where the real rescue came from. Not from time running backward, but from an honest accounting trick of genius. Keep the credit where it belongs, and the phone call's true legacy stays clean. It gave physics its language, not its cure. But a language is only as good as the sentences it gets right. And the 1940s handed the new language a test that nearly broke everything. Here is the honest version of that chapter, because a legend has grown around this story that gives the time reversal picture credit it did not earn. The equations of electrons and light had a disease. When pushed for high precision, they returned infinity as the answer to sensible questions. Not a big number, infinity, which in physics means the calculation has failed. The cure arrived in the summer of 1947, and it arrived on a train. At a small conference on Shelter Island off the coast of New York, an experimenter named Willis-Lamb presented an exquisite measurement. 2 energy levels in the hydrogen atom that the existing theory said should be exactly equal were not. They differed by a tiny, definite amount. The theory was wrong by a whisper, and now the whisper had a number. Hans Bethe, one of the great calculators of his century, boarded the train home, turning the problem over, and before the ride ended, he had found the move. The infinities, he realized, were piling into quantities we never actually measure on their own. Fold them into the measured values once, and every remaining prediction comes out finite, and, it turned out, breathtakingly correct. The technique came to be called renormalization, and that, not time travel, is what saved the physics of electrons and light. The backward-running positron made the bookkeeping elegant. The train ride made it work. The two together became quantum electrodynamics, the most precisely confirmed theory in human history. There is one more theorem from those years that belongs in your pocket for the final act, and it can be said without a single symbol. In the 1950s, several physicists, Gerhard Luders and Wolfgang Pauli among them, proved something remarkable about the deep rules of the universe. Any theory built on the foundations physics actually rests on, Einstein's relativity plus quantum mechanics, is required to treat a particle and its mirror twin with perfect even-handedness. Flip the charge, flip the handedness, run the film the other way, and the laws must read exactly the same. It is called the CPT theorem, and what it means for our story is lovely. The perfect match between the electron and the positron is not a coincidence physics stumbled on. It is a promise the mathematics makes. The experiments you are about to hear are humanity checking whether the universe keeps that promise. How precisely confirmed? This is where the story circles back to the sameness puzzle, with instruments Wheeler could only have dreamed of. First, understand the kind of machine involved, because it deserves a moment of wonder in its own right. Physicists learn to hold a single electron, one, alone, in a cage with no bars, woven entirely from electric and magnetic fields inside a vacuum colder and emptier than deep space, and to keep it there, one particle in captivity for months at a time. Held that way, the electron can be interrogated gently, over and over, its tiny magnetic personality read out to ever more digits, the way you might weigh a single coin 10 million times and average away every tremor of the scale. The theory predicts, and these machines can measure, exactly that magnetic property. In 2023, a team led by Gerald Gabriels measured it to about 1 part in 10 trillion, 13 digits of agreement, the most precisely known property of any elementary particle, and the theory and the measurement matched. And the same style of machine had already staged an even more pointed contest. In 1987, in Seattle, physicists held an electron and then a positron, alternately, in a single trap, and compared their magnetic properties head-to-head, matter against antimatter on one scale. They matched to about 2 parts in a trillion. Picture 2 coins, minted 80 years apart on different continents, weighed on a balance so fine it would notice a single missing atom, and coming out identical. That is how perfect the mirror between the electron and its backward twin is, as far as anyone can measure. At CERN today, the checking has reached a level that reads like science fiction written by an accountant. In a facility built to slow antimatter down rather than speed it up, physicists routinely manufacture whole atoms of antihydrogen, a positron orbiting an antiproton, matter's mirror rebuilt from scratch, atom by atom. The atoms are held in magnetic traps, a few dozen at a time, hard-won and precious, and then interrogated with lasers. Shine light on ordinary hydrogen, and it answers by absorbing very particular colors, a fingerprint chemists have known for a century. Antihydrogen, ask the same question, answers with the same fingerprint, matched in careful campaigns to about 2 parts in a trillion. Other experiments in the same hall have compared the proton and its mirror twin, and found their measurable properties identical to 16 parts in a trillion. Year after year, the mirror is polished harder and inspected closer, because any scratch, any tiniest mismatch between matter and antimatter's properties would be the discovery of the century and a crack in the deepest theorem physics owns. If the positron is the electron's reflection in the mirror of time, then the mirror, tested for decades, has yet to show a single scratch. Why does this matter for the phone call? Notice what this precision does to the idea's 2 halves, because it splits them cleanly. Everything about the mirror, Wheeler got gloriously right, or at least his picture sits perfectly on top of what the machines confirm. The positron truly is the electron's exact reverse, to every digit anyone can reach. But a perfect mirror says nothing about a single traveler. 2 genuinely different particles, related by the deep even-handedness of the laws, would look exactly the same in these machines as one particle meeting itself backward. The precision experiments crown the stolen half and stay silent on the wild half. To rule on the wild half, physics needed not a finer mirror but a census, and the census is coming. And what about the sameness itself, the identicalness that started all of this? It stopped being a philosophical observation and became a laboratory fact in 1987, in an experiment of almost absurd simplicity and bottomless depth. In Rochester, 3 physicists named Hong, Wu, and Mandel sent 2 identical particles of light, 2 photons, toward opposite faces of a half-silvered mirror, a piece of glass that gives each photon a 50-50 choice, pass through, or bounce. Two ordinary objects making independent 50-50 choices should sometimes leave in opposite directions. Flip two coins and you get one head and one tail about half the time. But when the two photons were made truly identical, arriving in perfect step, matched in every property, the experimenters saw something that still delights physicists to describe. The photons never left separately. Never. They always exited together, side by side, as if they had agreed. Picture two identical dancers entering a revolving door from opposite sides, and every single time, without exception, spinning out through the same exit. No conspiracy, no signal between them. Being perfectly identical, it turns out, changes what can happen. The universe computes the possibilities differently when there is no fact of the matter about which one is which, and the difference shows up as a measurable, repeatable refusal to separate. Let us be careful in the calm way this channel prefers. This does not show that the two photons are secretly one particle visiting the mirror twice. What it shows is stranger and more solid. It shows that identical in the quantum world means something no everyday object ever achieves. So utterly interchangeable that nature itself cannot, even in principle, keep track of which is which, and behaves accordingly. It is worth lingering one more beat on that experiment, because the fussiness it required teaches the lesson from the other side. Getting two photons to be genuinely identical is hard. They must match in color, in polarization, in shape, and they must arrive at the mirror at the same instant, to within a timing window almost too small to say aloud. The experimenters could tune this, nudge one photon's arrival slightly, and the two are no longer perfectly interchangeable, and the strange togetherness weakens. Nudge further, and it disappears entirely, and the photons go back to behaving like two coins, sometimes together, sometimes apart. Slide the timing back into perfect step, and the togetherness returns, every time, a dial you can turn between two different kinds of world. On one side of the dial, things with the faintest trace of individuality, obeying the statistics of separate objects. On the other, things with none, obeying statistics that have no everyday counterpart at all. That dial has since become a workhorse. Versions of this refusal to separate are used today to test the quality of photon sources for quantum technologies, because perfect indistinguishability is now an engineering requirement, a spec sheet item. The deepest strangeness of identity has become something technicians calibrate on a Tuesday. Here's the strange part, and it deserves its own sentence. In the quantum world, being identical is not a description. It is a force of circumstance that changes what happens. Nothing in ordinary life prepares you for that. Two identical trucks do not drive differently because they are identical. Two identical electrons do provably, measurably, repeatably. When the universe cannot tell things apart, it counts their possibilities differently, and the counting shows up in experiments as real as a photograph. Whatever the word individual means at the bottom of the world, it is not what the word means in a crowd. So, the scoreboard, 80 years after the phone call, reads like this. The backward-in-time picture of antimatter, adopted, drawn daily, quietly threaded through every particle calculation on Earth. The perfect mirror between electron and positron, confirmed to 2 parts in a trillion and still holding. The perfect sameness of all electrons, confirmed so deeply that identical particles visibly change the rules of chance. Every ingredient of Wheeler's wild idea checked and found solid. And now the question this whole story has been building toward, the one Feynman asked in his first breath, comes back to collect its answer. If one folded world line were really writing all of this, the forward crossings and the backward crossings should come in equal numbers. Electrons and positrons, half and half. So, how does the census actually come out? And the census question has an observational side too, because you can ask the sky directly. If the universe held equal amounts of matter and antimatter, tucked into separate regions, then somewhere those regions would have to meet, and the meeting places would announce themselves. Every contact between a matter cloud and an antimatter cloud would glow with the unmistakable light of annihilation, painting borders across the sky that gamma-ray telescopes could not miss. Astronomers have searched, patiently and over decades, from balloon-borne detectors to an instrument mounted on the International Space Station, sifting cosmic rays for stray anti-atoms. The verdict is quiet and consistent. No glowing borders anywhere out to the largest scales surveyed, and essentially no complex anti-atoms drifting in from elsewhere. Within everything we can see, the universe is made of matter, wall to wall. Whatever happened to the other half of the ledger happened everywhere, uniformly and very early. It comes out as a landslide, and the landslide has a story of its own, one of the strangest in cosmology. Rewind the universe to its first moments, when it was hot enough that matter and antimatter were being made and unmade everywhere, constantly, in equal and opposite pairs. As everything cooled, the pairs met and cancelled, matter and antimatter erasing each other flash by flash, and the bookkeeping should have ended at zero, a universe of pure light with nothing left to build with. That is not what happened, and the numbers say something astonishing about why. For roughly every billion pairs that met and vanished, one extra particle of matter, just one, had no partner to cancel against and survived. Everything you have ever seen, every star, every stone, every person, the iron in your blood and the calcium in your bones, is built entirely from those 1 in a billion leftovers. The rest of the early universe's substance became light, and that light is still out there, cooled and stretched, filling the sky. For every atom's worth of survivor matter, about 1 billion particles of that ancient light still stream through space. The universe kept the receipts. Take one slow look at what that 1 in a billion arithmetic means for you personally, because it is easy to hear the number and miss its address. The atoms of your body are not generic matter. They are, every one of them, the unmatched remainder, the particles that stood at the end of the universe's opening annihilation, with no partner left to cancel against. Out of every billion participants in that first fire, roughly 1 walked out. You are built exclusively from the ones that walked out. And the light released by all the cancelled pairs did not vanish either. It is still everywhere, cooled by the expansion of space into a faint microwave glow that fills the sky in every direction. About 1 billion particles of ancient light for every particle of surviving matter. The receipt still attached to the purchase. When you feel the warmth of anything, you are downstream of a ledger that closed 13 billion years ago and left almost nothing. And the almost is everything. Why does this matter for the phone call? Because it is the verdict. The cosmos is not half matter and half antimatter. It is matter, essentially wall to wall, with antimatter appearing only in rare, fleeting flickers, in cosmic ray strikes, in certain radioactive decays, in hospital machines we will meet shortly. Wheeler's one electron, to be every electron, needed the backward crossings to match the forward ones, and they do not match. They do not come close. Feynman's objection, asked in seconds by a 21-year-old on a telephone, turned out to be the exact blade that ends the literal version of the idea. And Wheeler's improvised patch fared no better. Maybe the missing positrons are hidden in the protons, he had shrugged, and for a few decades no one could actually check. Then physics learned to look inside protons, firing electrons through them at enormous energies and reading the scatter, the same logic by which an earlier generation had discovered the atom's nucleus. The proton's interior turned out to be a seething, intricate place, but its contents are quarks and the glue that binds them. There are no hidden positrons in there, not one, and the books do not balance anywhere else either. The one-electron universe, taken literally, is wrong. Physics does not say so with anger. It says so the way it says everything, with a count. And there is a second, quieter blow to the literal picture, one that even Feynman's phone objection missed, and it comes from ordinary radioactivity. The one-electron story needs the universe's electron count to be fixed. One thread, however folded, crosses today's page a definite number of times. But the universe's electron count is not fixed. Inside certain unstable atoms, a neutron will, of its own accord, transform, and in the transformation, a brand new electron is made, on the spot, where none existed a moment before, and flies out of the nucleus. This is not exotic. It is happening right now in the potassium atoms of a banana, in the rocks under your feet, in your own body at a gentle background rate. Electrons are also destroyed, absorbed in other nuclear processes, erased from the count. Born and erased, continually, everywhere. A single immortal thread cannot have its crossings appear from nowhere and vanish into nothing. A real ledger of births and deaths demands something that can produce and retire electrons on demand. Hold that requirement, it is about to be paid in full.
And yet the puzzle that started everything still stands, sharper than ever. The electrons really are all perfectly identical, the newborn ones indistinguishable from the ancient ones, which only deepens the mystery. Even the electrons made fresh this morning inside a banana match every electron in the farthest galaxy to 13 digits. If they are not one particle, what are they? Here is the answer modern physics actually gives, and the lovely thing is that it keeps the heart of Wheeler's idea while letting go of the knot. First, get comfortable with the word field, because it names something more ordinary than it sounds. The air pressure in your room is a field. At every point in the room it has a value, everywhere at once, invisible, continuous, and entirely real, as your ears prove every time weather moves through. Physics discovered across the 20th century that reality at its base is built this way, not out of little objects scattered in emptiness, but out of continuous, space-filling somethings, fields, whose local flickers and knots are what we call particles. Now picture a drum, a single vast drum skin, stretched taut. Tap it here, and a small dimple of vibration appears. Tap it there, another. Tap it in 1,000 places and you have 1,000 vibrations, each one local, each one countable, each one able to move and interact. Now ask, why is every dimple the same kind of thing? You would never puzzle over it. Of course they match. They are all vibrations of the same skin. There is only one drum. Modern physics, in the framework called quantum field theory, says the universe works this way. Underlying all the electrons, there is a single universe-spanning something, the electron field, filling every cubic centimeter of space, from the room you are in to the farthest galaxy. What we call an electron is a little localized vibration of that one field. 100 billion trillion 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 vibrations, one field, trillion trillion vibrations, one field. The electrons are identical for the same reason every ripple is made of the same pond, the same reason every note from one bell carries the same voice. They are not copies of an original, they are notes from the same underlying instrument. And watch how gracefully the field answers every riddle this story has raised. Why are all electrons identical? Because every dimple of one drum skin is a dimple of that skin. There is nothing else for it to be made of. Why can electrons be born in a decaying nucleus and destroyed in another? Because a field can always be tapped somewhere new, and a vibration can always fade. Births and deaths are just the skin stirring and settling, with no unbroken thread required to do the accounting. Why did Wheeler's backward-in-time picture work so beautifully as a tool? Because the field's mathematics genuinely contains that symmetry. The backward reading is a true feature of the drumskin's rulebook, which is why Feynman could compute with it forever without it ever being literally about travel. Even Feynman's fatal census objection dissolves. The electron field and its vibrations are free to outnumber the antimatter vibrations, because nothing ties their counts together the way one folded thread would.
The field picture keeps every success of the phone call and pays every one of its debts. That is what a right answer usually looks like in physics, not the destruction of the beautiful wrong idea, but its promotion into something that can actually carry the weight.
Here's the strange part. Look at what just happened to Wheeler's idea. He said the electrons are all the same one thing, and he was wrong about the geometry, wrong about the backward loops balancing, wrong about the count. But squint at the field picture and you can see his guess standing there, transformed. There is, in a precise sense, one electron thing in the universe. It is not a particle threading a knot. It is a field filling all of space, and every electron that has ever existed, including everyone in you, is a temporary stirring of that single, shared, universe-wide entity. The phone call reached for one and grabbed the wrong one. The universe, it turns out, had a one to offer after all. It was just bigger, stranger, and quieter than a particle. Not one traveler crossing the field of snow, but the field of snow itself, everywhere at once, in which every footprint is a moment of the same ground rising. Before the meaning, pause and look around the room you are in, because everything this story has taught is present, right now, in the most ordinary furniture of your evening. The lamp beside you is pouring out particles of light, each one a stirring of a universe-wide field. The wall behind the screen holds its shape, refuses to let your hand pass through it, because its electrons, identical to the last digit, are enforcing the no two alike seating rule that gives matter its solidity. The warmth of your own skin is chemistry, and the chemistry runs on the perfect interchangeability of parts that this whole story has been about. Nothing in the room is exotic. Everything in the room is running on the physics of the phone call. That is the strange generosity of fundamental science. It is never about somewhere else. Step back now, because with the whole story on the table, you can start asking what it means, and the meaning begins somewhere unexpected, in a hospital. Every day, in ordinary buildings in ordinary cities, medicine runs on antimatter. A patient having a certain kind of scan is given a gently radioactive tracer, and as it decays inside the body, it releases positrons, real ones, each of which travels a hair's breadth before meeting one of the body's own electrons. The pair vanishes in a tiny flash of light, and here is the elegant part. Not one flash, but two, thrown out in exactly opposite directions, like a clap sending sound both ways down a hallway. The machine is a ring of detectors surrounding the patient, and when two detectors on opposite sides light up at the same instant, the machine knows an annihilation happened somewhere on the straight line between them. Collect millions of those lines and the lines crosshatch into a living map of the body's tissues, drawn entirely by matter meeting antimatter. The scan is called PET, and the P literally stands for positron. Think about what that means for tonight's story. The particle that Dirac's arithmetic demanded, that Anderson photographed falling from the sky, that Wheeler cast as a time traveler and Feynman drew backward in every diagram, now quietly helps find tumors on a weekday morning. There is no better reminder that even the strangest physics has a habit of ending up in the room with you. And here a fair viewer, remembering the backward in time picture, asks the question that deserves a plain answer. If antimatter really can be described as matter moving backward through time, and hospitals make antimatter every day, can something be sent backward? A message? A warning? A lottery number? The answer is no, and the reason is worth understanding rather than just accepting. The backward in time picture is like a photograph negative, a completely faithful, completely usable second way of describing the same picture. Every calculation done in the backward language gives exactly the same predictions as the ordinary forward language, the same causes leading to the same effects in the same order for every observer. Nothing in it opens a door, it re-describes the hallway. Physicists keep the picture because it makes the arithmetic beautiful, not because the past has a mail slot. The universe, as one physicist quipped, appears to be run by an agency that keeps history safe. You can describe yesterday from a strange direction, you cannot revise it. So the tools are real, the mirror is flawless, and the count killed the literal one electron. What survives of the phone call's deepest provocation? One thing survives, and it is the thing this whole evening has been circling, the sameness itself and what it whispers about you. Because you, whoever you are, wherever you are watching this, are built from these particles. The electrons doing the chemistry in your eyes as you read this, the ones carrying the nerve signals that are, this instant, letting you understand this sentence. Every one of them is a vibration of the same universe-spanning field as every electron in every person who has ever lived. Not similar to theirs, indistinguishable from theirs, in the deepest sense physics knows. If you could reach into your own hand and lift out a single electron, and reach across history into any other human being, a stranger on another continent, a scribe in ancient Egypt, the first person who ever looked up and wondered, and lift out one of theirs, then no experiment could tell you which was which. No instrument, no conceivable measurement. The parts of you carry no names. The parts of everyone carry no names. At the level of the particles, the universe does not file anyone separately. Here's the strange part, and it is the calm, honest heart of this video. Physics stops exactly there, and something in us wants to keep walking. If the pieces are utterly interchangeable, a quiet voice asks, then what exactly makes me a separate someone? Is the boundary between my experience and yours as fundamental as it feels? Or is it more like the boundary between two ripples on one pond, real as a pattern but not written into the water itself? You should know that serious thinkers have mapped this territory carefully, and that the map has three regions. The everyday view, the one nearly everyone holds without ever naming it, philosophers call closed individualism. You are one continuous self, from birth to the end, distinct from every other. A second view, associated with the philosopher Derek Parfit's famous puzzles about personal identity, is stranger. Perhaps there is no persisting self at all, only a chain of momentary experiences, each linked to the next like frames of a film, with the feeling of a continuous you being something the frames generate. And the third view is the one this video's title gestures at. In philosophy, it is called open individualism, explored by the philosopher Daniel Kolak in a book bluntly titled I Am You, and before him by Arnold Zuboff, who called it universalism. The proposal, the boundaries between persons are, in some deep sense, an illusion, and consciousness, wherever and whenever it lights up, is one and the same subject looking out of different windows. The philosopher Thomas Nagel has described this family of ideas as a radically original conception of the mind. If it were true, every act of kindness ever done and every hurt ever inflicted would have the same strange shape, the one experiencer meeting itself. And now the sentence this channel owes you, delivered as plainly as it can be said. That is philosophy, not physics. No measurement supports it, no measurement refutes it. The indistinguishability of your electrons is a laboratory fact. The identity of persons is a question about minds, and minds are not particles. Between the fact and the idea lies a leap no experiment has ever licensed. Some viewers will feel the leap is obviously too far, and their case is strong. A person is their memories, their relationships, their one unrepeatable path through the world, and the sameness of parts says nothing about the separateness of wholes. Two houses built from identical bricks are still two houses. You can live in one and not the other, and no inspection of the bricks will ever blur that difference, because what makes a house that house is the arrangement, not the material. On this view, you are your arrangement, and your arrangement is gloriously, unrepeatably yours. Other viewers will feel the leap is strangely small, and their case has its own pull. Play the same piece of music on two pianos, and there are two performances but arguably one song. Once the universe declines to label the pieces, they suspect, the labels on the people start to look like something we added ourselves,
a habit of grammar mistaken for a fact of nature. Zuboff, back in 1990, pressed the thought in an essay whose title says it all, Oneself, arguing that what looks out from behind every pair of eyes may be one and the same experiencer. Physics does not vote. Take a moment, genuinely, and notice which way your own intuition leans, and then notice, honestly, that your lean is a feeling, not a finding. That noticing, more than any answer, is what this final stretch of the story has to teach. It is worth being honest that scientists have occasionally wondered aloud in this direction, and equally honest that wondering is all it has ever been. What the science gives you is not an answer. It is a genuinely open question, sharpened to an edge no generation before ours could have cut. The universe keeps no records that distinguish your smallest parts from anyone else's, and it is silent about what that means for the you that is reading this. Some have hunted for a bridge between the quantum world and the mind itself, and since this video promises honesty, here is the state of that hunt, briefly and without drama. A well-known proposal by the physicist Roger Penrose and the anesthesiologist Stuart Hameroff suggests that consciousness might involve genuinely quantum processes in tiny structures inside neurons. Most physicists are skeptical, for a solid reason. The warm, wet brain is spectacularly good at destroying delicate quantum states, on timescales so short that, by standard estimates, no quantum subtlety should survive long enough to matter to a thought. The proposal's defenders have pushed back with revised numbers, and in recent years laboratory work on those neural structures has reported curious light-handling effects in isolated samples. It is a real, live, contested corner of science, and nothing in it, nothing, connects one person's mind to another's, or supports the idea that a single particle carries every consciousness. If that bridge exists, no one has found so much as its first stone. The honest map shows a laboratory fact on one shore, a philosophical question on the other, and open water between.
Why does this matter if the biggest question stays open? Because of what the sameness does every second, whether or not anyone is watching. The perfect identity of electrons is not a curiosity. It is load-bearing for your existence in the most practical way imaginable. Because all electrons are identical quantum objects of a particular kind, they obey a rule with no exceptions. No two of them in an atom will settle into exactly the same state, the same little slot of energy and motion and spin. Think of an atom as a small hotel with strict management. Every room is unique, and no room is ever double booked. Electrons arriving at an atom must each take a different room, filling the hotel floor by floor. That single rule is the reason atoms have structure at all, the reason carbon bonds the way it bonds, the reason chemistry exists, the reason molecules, proteins, cells, and you exist. If electrons were even slightly distinguishable, even one part in a trillion different from each other, the hotel rules would loosen, the floors would collapse into the basement, and the periodic table, and everything built from it, would not be here. The sameness that launched a strange phone call in 1940 is, quite literally, what your body is standing on tonight. Walk that idea up through the elements once, slowly, because it turns the driest chart in every classroom into something almost musical. Hydrogen, one electron, one guest, ground floor, the simplest hotel there is, and most of the universe is exactly this. Helium, two guests, and the ground floor is now precisely full, which is the entire reason helium is aloof, unreactive, content, the noble gas that bonds with nothing. Its hotel has no vacancies to offer. Then the floors climb. Carbon arrives with a half-filled upper floor, 4 rooms spoken for and 4 standing open, and that particular incompleteness, that specific pattern of vacancy, is what makes carbon the great connector, willing to link with itself and with others into chains, rings, lattices, the endless scaffolding of every living thing. Oxygen's eagerness, iron's temperament, gold's reluctance, every chemical personality in the universe is nothing but a seating chart.
enforced by the rule that no two identical electrons may take the same room. Read the periodic table this way and it stops being a list. It is the complete catalogue of what one rule about sameness builds when you give it a universe to work with. And the rule only holds because the guests are perfectly, absolutely identical. Distinguishable electrons could share rooms, and the whole architecture would slump into featureless collapse. Chemistry, biology, the smell of rain, the taste of bread, the reader and the read, all of it is carried on the fact that the universe cannot tell its electrons apart. Why does this matter as more than poetry? Because it hands you a way to feel the answer to a question people sometimes ask about fundamental physics. What difference does it make whether electrons are identical, or fields are real, or antimatter runs backward on a diagram? The difference is not somewhere far away in a laboratory. The difference is that there is a you to ask. Change the 13th digit of the electron's sameness, and the universe keeps the stars but loses the chemistry, keeps the hydrogen but loses the hands, the harvests, the questions. The deepest facts are not the furthest ones. They are the ones so close, so constantly load-bearing, that it took our species until 1940 to notice there was anything to explain.
One puzzle may still be nagging you, and it deserves a plain answer before the close. If the smallest parts of the world are this strange, indistinguishable, refusing to separate on mirrors, describable backward in time, why does your everyday world look so ordinary? Why does your coffee cup sit in one place, with edges belonging unambiguously to you? The answer is one of the quiet triumphs of modern physics, and it can be said without equations. Quantum strangeness depends on privacy. The moment a system's alternatives get recorded by its surroundings, bumped by air molecules, struck by light, warmed by contact, the strangeness washes out, and this happens fast beyond imagining. For anything big enough to see, the washing out is complete in a sliver of a second, so small it has no everyday name. A dust mote floating in sunlight has its position broadcast to the universe billions of times over before you can blink. So the world of cups and tables is not a different world from the quantum one. It is the quantum world with all its secrets continuously published, and published things behave classically. The strangeness never left. It just cannot keep anything to itself at your scale. And that, incidentally, is the honest physics reason why no quantum thread can plausibly run between minds. For the parts of two brains to share one delicate quantum state, that state would have to stay private, unrecorded by the warm, wet, busy environment of biological tissue. By the standard estimates, such privacy survives in a brain for less than a trillionth of a second, gone before a single thought can begin. Some researchers, as we said, can test pieces of this and keep probing. But as the accounts stand, whatever unity of consciousness might or might not exist, quantum mechanics is a poor courier for it. If the deep question of this video has an answer, physics is telling us to look for it somewhere else. This is the part I find hard to stop thinking about. We began with a claim that sounded like a joke, one electron pretending to be all of them, and every step we took to test it made the world stranger rather than tamer. The joke was wrong, but it was wrong the way a good compass is wrong about the room while being right about north. All electrons really are, in the field picture, expressions of one thing. Antimatter really is, in the working language of physics, matter read in the other direction of time. And identity, at the bottom of the world, really is not what everyday life assumes. There are no name tags down there, none, and there never were. Wheeler fired his guess into the dark and hit, not the target he aimed at, but a deeper one behind it. Could anything reopen the case? Honest science always names the door, so here it is. If any experiment ever catches the mirror scratched, an electron and positron differing by any amount in mass or magnetism or the colors their atoms shine, the deep theorem behind the mirror breaks, and with it a foundation stone of modern physics.
and every story told tonight gets rewritten by whoever finds the scratch. The trap builders and the antihydrogen teams are looking, full-time, right now, pushing the comparison one digit further each decade, and so far the mirror holds. That is not a formality. It is the difference between a closed legend and a living investigation, and this one is alive. The strangest idea of 1940 is still, in 2026, employing people to try to break it.
And what of the two men on the phone? Their partnership outlived the idea by half a century. Wheeler went on scattering sparks for the rest of his long life, naming the black hole, mentoring generations, cheerfully proposing outrageous things into his 90s. He never did publish the one-electron idea, and by every account never quite believed it, which may be the most charming part of the story. He needed it to be interesting, not true. Feynman carried the stolen half to Stockholm and carried the phone call itself as a treasured story, retelling it with full credit in front of the world's assembled scientists at the very peak of his own triumph. There is something quietly instructive in that too. The idea failed, the gratitude did not. In science, at its best, being usefully wrong is a form of greatness, and both men knew it. There is one more figure in this story who deserves the closing stretch, and it is the man who asked the fatal question and stole the useful half. What Richard Feynman did with Wheeler's phone call is a masterclass in how to think, and it is teachable in one sentence. He kept the tool and released the belief. He did not fall in love with the beautiful idea, and he did not sneer at it either. He tested it in seconds against a fact he knew, watched the grand version fail, and then noticed that one gear inside the wreck still turned, and built the best confirmed theory in the history of science partly out of that gear. Years later, he could laugh about it in Stockholm, giving Wheeler full credit for the spark, while keeping full honesty about the flaw. If a viewer takes one habit away from this entire story, let it be that one. When you meet a beautiful idea, you do not owe it belief, and you do not owe it scorn. You owe it a fair test, and the humility to keep whatever survives. Return, one last time, to the field of snow. When this story began, the footprints crossing it were a riddle. Thousands of tracks, all pressed by what seemed to be the same boot, and Wheeler's answer was a single, tireless walker, looping through the field along a path no one could see. The answer physics settled on is quieter and, in its way, larger. There is no lone walker. There is the snow itself, one unbroken white expanse from horizon to horizon, and every footprint, every electron, every particle in every hand that has ever been held, is a place where that single expanse was pressed into a shape for a while. The prints are countless, the snow is one. Wheeler aimed at the wrong oneness and hit the edge of the right one, and physics has been walking that field ever since. So let the whole story settle into place, the way a long walk settles when you finally sit down. In 1940, a phone call proposed that every electron in the universe is one particle, threading forward and backward through time. The backward-in-time picture of antimatter, born in that call and in Ernst-Stueckelberg's careful papers, proved true enough to power quantum electrodynamics and every Feynman diagram drawn since. The perfect mirror between matter and antimatter has been confirmed to a couple of parts in a trillion. The perfect sameness of electrons has been confirmed so deeply that identical particles change the very rules of chance on a half-silvered mirror. And the literal one-electron universe died at the hands of a count, the one in a billion surplus of matter that everything you love is made from. What replaced it is not smaller. One field, filling all of space, of which every electron that ever was, including every one of yours, is a passing vibration.
The universe declined to be made of one particle. It settled for being made of one instrument.
If you found value in this exploration, consider subscribing. It helps these calm journeys through the strangest questions reach more curious minds. If a friend asks you tomorrow what this video actually claimed, here is the honest sentence to hand them, and it is worth getting right. Physics has confirmed that every electron in the universe is perfectly interchangeable with every other, that antimatter is matter's exact mirror, describable as motion reversed in time, and that all of it is best understood as ripples of a single field filling all of space. Physics has not confirmed, and cannot currently test, whether that deep oneness of parts says anything at all about the oneness of persons. One sentence of solid ground, one sentence of open sky. Most stories about the universe are all one or all the other. The good ones, like this one, teach you to feel exactly where the ground ends. And the question the title asked, whether your life is every human who ever existed. Physics, after 85 years, answers exactly none of it. And that refusal is the most honest gift this story has to give. What physics hands you instead is a fact to carry. The smallest parts of you are indistinguishable, in principle, forever, from the smallest parts of every person who has ever drawn breath. Whether the boundary between you and them is a wall or a ripple, no instrument can say. Somewhere in Princeton, on a spring evening in 1940, a telephone rang with a wrong answer to the right question. The phone call ended 85 years ago. The question tonight is still on the line.